Hello, physicists. It's Mr. Gopal here with a lesson from the Modern Physics Unit. Specifically, I want to talk today about the quantum mechanical atomic model. This is a model that replaced the Bohr model of the atom as the most accurate description of an atom. All right. But before we get into that, we need to review the Bohr atom itself. So Bohr's atomic model started off with the idea of a nucleus filled with protons and electrons. Here it is in red. And then a series of energy levels, as we called them, that held electrons that orbited that. And so actually, I'm going to clear this lest we forget Rutherford's famous experiment in which he discovered that our nucleus is very tiny and that these energy levels of electrons are quite far away. This aspect of the atomic model has been maintained. So if we had, say, a couple energy levels here, all right, this would be roughly what the Bohr model would say is going on. And let's say that we had 2 electrons in the inner one, followed by 8 in the outer one, all right? 4, 5, 6, 7, 8. Okay, that would make a total of 10 electrons. In order for this to just be an atom and not an ion, we would have 10 protons, probably 10 neutrons as well. Although as we know from chemistry, the number of neutrons can differ for different isotopes of an atom, which would be different versions of an element that have different amounts of neutrons per atom, all right? So if this is 10, we're talking about neon, or Ne. Got 10 protons, 10 neutrons, and 10 electrons. In the Bohr model of the atom, electrons orbit in fixed orbitals around the nucleus, all right, where they can always be found. If we energize an electron, it will jump from an inner to an outer energy level. However, if it jumps out, it will become increasingly unstable. And then when it jumps back, due to the instability and how hard that is to maintain, it will give off light. Okay, so at this point, light is emitted when energy is released. Final thing I want to say about that model is that Bohr said that the amount of energy an electron had was a fixed quantity depending on which energy level it was in. So if you recall, in a previous video, we examined these things. If I look back at our reference table, we can see, it's right here, that we can measure in electron volts the amount of energy a given electron has, all right, depending on which energy level it's in. And if you recall, we were calculating changes in the amount of energy depending on how much an electron was energized and therefore which energy level it moved into, and therefore how much energy it gave off when it moved back down to a state of stability. Now, the thing about the quantum mechanical model is that it was born out initially from the idea that nature is symmetric. We knew that electromagnetic radiation, for example, a light wave, had properties that could be described as a wave, but at the same time had properties that could be described as particle-like, all right? And this leads to an interesting duality that they talk about in this lesson called wave-particle duality. I'm going to go to that slide. And so what they discuss here in the lesson is that the wave-particle duality of electrons makes it impossible for us to find the actual location of an electron while accurately measuring its energy. We can either know a lot about one aspect, like its energy, and a little bit about its position, its particle behavior, or we can know everything about its position, all right, but we can know very little about its energy. And the reason why is because we have a completely different set of equations when it comes to describing waves, some of which you may remember, which relate to a wave's wavelength, frequency, and periodic behavior. All right, and on the other hand, when we talk about its position, we're talking about its mass and its location. And if you recall also, we have accepted that an electron has a definitive mass and therefore can be described as a particle as well. In other words, it has mass and it takes up some space. Now, you might be asking yourself, what's the big deal? And also, if the person who proposed this, who was a physicist actually doing his graduate thesis named de Broglie, if de Broglie proposed this and said that actually not only is it electrons that behave this way in electromagnetic radiation, but everything in nature, why don't we see wavelengths coming out of all types of objects? Why am I not looking around this apartment seeing wavelengths pouring out of every object? Now, the reason is because we describe the relationship between wavelength and the momentum or energy of an object in terms of the following equation. I'm going to write it in the blue box here in red so we can see it very well. Ooh, get back here. And that equation is lambda is equal to h over p for momentum. All right. And so in this equation, we say that lambda equals wavelength. We say p equals momentum. And then finally, we say that h is Planck's constant. Now, if we go back here, we can find Planck's constant. It's right here. Oops, sorry. Here's Planck's constant. It's 6.63 times 10 to the negative 34th joule seconds, all right? And it is a constant that allows us to explain a lot of subatomic behavior, but we can apply it to all objects. And now I'm gonna get to answering our question. I apologize for doing that. I'm gonna write it again. So we know that wavelength equals Planck's constant over momentum. And so if we wanted to say calculate the wavelength of a bowling ball, all right, that is moving at a certain speed, we can calculate it based on that bowling ball's mass and its speed. So let's say that bowling ball weighs, I don't know, 3 kilograms, all right? So mass of this bowling ball is 3 kilograms. And its speed or its velocity is 10 meters per second. I can do a simple calculation of its momentum. I can say its momentum is equal to its mass times velocity, which equals 3 times 10, or 30 kilogram meters per second. Now, in order to calculate its wavelength, what I need to do, I'm going to do it over here. So I'm going to say its wavelength has to be equal to Planck's constant divided by 30. All right, so again, Planck's constant is 6.63 times 10 to the negative 34th joule seconds. All right, so I'm going to put that number on top. Sorry, slide moved. .63 times 10 to the negative 34th joule seconds. And I'm going to divide that by 30 kilogram meters per second. And so the wavelength that this bowling ball emits will be the quotient when I divide these two things. And I already did it, so I can give you the answer. It's going to be a whopping 2 times 10 to the negative 35th meters, all right? Remember, recall from the wave unit, we measure wavelength in meters. It's the actual physical length of a wave, all right? Now, I don't know about you, but I cannot see objects that are that small. So the bowling ball indeed is giving off a wavelength. However, it's microscopic. We can't see it with the naked eye, all right? So this is my first proof that yes, there is something going on. Once again, just like the fact that my computer is made up of billions of atoms, trillions of atoms even, and I can't see them vibrating against each other. What I see is the computer composed together in a fixed state, all right? In much the same way, the bowling ball gives off a wavelength, but I cannot see it. So particles all have wave-like characteristics, and waves all have particle-like characteristics. Hopefully that helps solve that mystery. Now, the other aspect of the quantum mechanical model, illustrated in these slides here, is that we have certain areas where we can find our electrons. So because it behaves like a wave and a particle, we can't calculate all of its features at once, and we can only put a probability on its location. That probability puts it in a certain area, and that area is described in 3 dimensions by these orbitals, all right? And these orbitals are what make up the larger energy levels that Bohr came up with. So those energy levels are accurate descriptors for what's going on inside the atom with electrons. However, they themselves have sublevels that we call orbitals, all right? These are examples of what we call p orbitals, but then we also have d orbitals and f orbitals, and we also have s orbitals, which are very simple. They're spherical in shape, all right? And so we don't need to get too much into it because the math in terms of actually finding or a probability for the location of an electron is very complicated. What we need to understand on a basic level is the Bohr model had electrons traveling in a fixed path, and the wave, the quantum mechanical model does not have that. It has a probability of an area in 3 dimensions, a volume, I guess you could say, where you can find an electron at any given moment, all right? Now, the final crucial thing to understand about these suborbitals is both their name and which ones compose each overall energy level. So again, if we're thinking about the Bohr model, all right, we have these larger energy levels. They're described on the periodic table. So the first energy level just holds 2 electrons, if you recall. And hydrogen and helium are the 2 elements that only have a first energy level. Everything with more electrons has at least 1 more energy level, the second one. And the second one is composed of S and P. If you recall the drawing that I made at the beginning of this video, we were talking about neon, all right? And neon has a total of 10 electrons. Obviously, the first 2 are going to be in that S sublevel, and the remaining 8 are going to be in that P level, okay? And so, well, actually, no, I'm sorry. It's not exactly like that. Let me expand this so we can see it a little bit better. Here is the tricky thing. There we go. All right, so the first energy level only has an S sublevel. The second energy level has both an S and a P level, all right? Now, in this one, we know the maximum amount of electrons we can have is 2. So we know the S holds 2. Now, the S is holding 2 as well in the second energy level, and the remaining 6 are held in the P sublevel, all right? And now if we think about this one again, or sorry, the next level, we can have 2 in the S, we can have 6 in the P, and moving up by 4 again, we can have a total of 10 in the D, all right? And so if we add up everything in total in the second energy level, that's going to be 2 plus 6 or 8. And if we add up everything in total in the third energy level, that's going to be 2 plus 6 plus 10 or 18. All right. That's as far as I want to go for right now. because that describes a lot of the elements that we discussed in chemistry and all of the elements that we revisited in physics, all right? So we know the first energy level in total holds 2 electrons. The second one in total holds 8 electrons. The third one in total holds 18. And the other thing that we need to understand about it is that these energy levels are broken into sublevels of different shapes, 3-dimensional shapes, and there's a probability that electrons are floating inside that 3-dimensional shape, all right? The final thing that I want to go over is just one of the questions that you're given that is somewhat Regents-based. Now, you don't need to understand the finer nuances of the quantum mechanical model in Regents physics. What you do need to understand is how to work with these sublevels and energy levels overall. So just keep it in the back of your head. S sublevel holds 2 electrons at max. P sublevels hold 6 electrons at max. D sublevels hold 10 electrons at max. Now to the questions. So if we're talking about what the total number of electrons in the p orbital of the second energy level is, then we know that we're talking about 6. The reason I know this, again, I'm going to write it here. S sublevel hold 2 electrons. P sublevels hold 6 electrons. D sublevels hold 10. If we wanted to go farther, we would increase by 4 again, because F sublevels hold 14 electrons. And so we can say that the total number of electrons in the p orbitals of the second energy level is 6. Most of the Regents-based questions about this go no farther than remembering the amount of electrons in each particular sublevel. And let's think, before I end this video, let's just think very carefully about the things that we covered today. For one, we discussed why we have both wave-like characteristics on the one hand and particle-like characteristics on the other hand when we discuss all objects, including electrons. And I used the example of a bowling ball to illustrate why there is a wavelength, all right, but we cannot see it. And this is the case for most objects because they are traveling far too slow for us to be able to see their wavelength, all right? Now, the other thing to mention is that we discussed that there's a probability of finding an electron in a certain area, and it does not travel in an exact circular path or circular orbit around the nucleus. In fact, it travels in a certain 3-dimensional area that we can describe with as an S area, a P area, a D area, or an F area, all right? And each of these areas can hold at maximum 2, 6, 10, or 14 electrons. Now, why is all of this so valuable? Well, because it helps us predict the behavior of atoms and electrons so much better. And it also helps us describe the world around us better. At times, it's going to be of maximal importance that we can use wave energy equations and models to describe behavior. On the other hand, very often, as we've seen in this course, it is very helpful to describe things as particles with mass that take up space. And so that is my lesson on the quantum mechanical model. So much more to learn, but I'm going to leave you there, and I look forward to being again with you soon.